In part 4, instead of going ahead and talking about the acceleration analysis of the Hooke's joint, we will now get into the actual mechanical analysis, the mechanical inference or the mechanical intuition, what we want to derive. What is it that we understand from this equation, especially about the output speed? Now, let me revise that in this equation, shaft angle alpha is a constant. Theta is the angle turned by the input shaft, which is from 0 to 360. So this term is continuously changing. Then angular velocity omega 1 is the speed of the input shaft, that is constant. So omega 1 is a constant, alpha is a constant. We have managed to get angular velocity 2 of the output shaft directly depending upon the rotation of the input shaft. So as the input shaft angle theta changes, output shaft speed changes according to this rule. Now what we are interested in knowing is there a case where the input and the output shaft are having the same speed? Now remember, the input shaft is continuously rotating at the same speed, which is constant, which is omega 1. The output shaft, while rotating, the speed is increasing or decreasing. Now, at what point while rotation does the input speed and the output shaft speed become equal? Let's call this as case 1. And in case 1, let us say that omega 1 and omega 2, let it be the same, which means input velocity and output shaft velocity, let's assume this is the same. Our intention is to find when is this the same. Now, very simply, if you put this ratio in this third equation as 1, you will get a very simple cos alpha divided by 1 minus cos square theta sine square alpha, because I want the ratio to be 1. Now, let's cross multiply this. 1 minus cos square theta sine square alpha in the numerator is equal to cos alpha. Now, if I rearrange the terms, because finally I want to get theta on one side and everything on alpha on the other side, then cos square theta sine square alpha can be written as 1 minus cos alpha. Very simple algebra I have done. I have shifted cos alpha on this side, so it looks like 1 minus cos. And I have shifted this 2 product on the other side, so the minus has become plus. Now, one last step. Simple cos square theta on one side would be 1 minus cos alpha divided by sine square alpha. I'm sure by this time you should have seen how this can be simplified. So we will keep the 1 minus cos alpha in the numerator as it is, and denominator we would replace by 1 minus cos square. Let's do it a bit faster. This looks like a square minus b square, so we can find the factorization of it. Again, numerator as it is, denominator a minus b and a plus b. This way your 1 minus cos alpha terms gets cancelled and cos square theta can be written as 1 plus cos alpha. This is some condition which we get. Now, which means if I know the shaft angle alpha, which is before the Hooke's joint starts rotating, the output is my black pen, this is the shaft angle between the input, if I know this angle, and if I substitute it in this equation and solve, whatever theta I will get, at that theta position of the input shaft, my output and input speeds will be the same. So I'm sure you understand by this time, we are trying to correlate the position of the input shaft to the speeds of the two shafts. Now, to make this equation a bit simpler, let's rewrite the numerator as cos square theta plus sine square theta, which is definitely 1, and let's keep the denominator of 1 plus cos alpha as it is. When you cross multiply, cos square theta into 1 will remain as cos square theta. Cos square theta into cos alpha would remain thus. This is the product. And right hand side is cos square theta plus sin square theta. So this term gets cancelled. You will be left with tan square theta, because I would shift this cos square theta on the down, is equal to cos alpha, and I will get a very simple condition that tan theta is plus or minus square root of cos alpha. This is the easier condition, although if you notice all these conditions are exactly the same. So every step equation is actually the same trigonometrically. We have adjusted, instead of this complicated thing, we have adjusted it to a simpler one. Now I will say that we substitute the shaft angle which is given to us in a problem. We will get a plus and a minus, which means we get two values. And if we find tan inverse of this, we will get actually 4 values of theta which satisfy this equation. So there are 4 possible values of input angle theta which satisfy this equation, such that angular velocity of the output shaft becomes equal to angular velocity of the input shaft. End of part 4.